Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 4 of the lecture on the regional skew. Right, this is the 10th lecture in the course on statistical methods in hydrology. On our list of topics, we're down here at the bottom on updated methods of estimating regional skew. So in video 3, we talked about the methods within Bulletin 17B that were suggested for doing regional skew studies. And the second method was developing prediction equations using linear regression, right? Equations to relate the skew coefficients to watershed variables such as drainage area, average slope, percent lakes, any of those things that we described in the second video as explaining the skew coefficient. So the way these studies worked was that for all of the gauges in the region, the skew coefficient was computed. And for the same watersheds that these gauges were in, the values of these watershed variables were computed as well, the drainage areas and the average slopes. And then a regression analysis was performed to develop regression equations to compute skew as a function of some of those explanatory variables. So one of the difficulties with using regression for an analysis like this is that there's many assumptions in regression, and not all of them are easy to meet. So ordinary least squares regression is that first regression method that you would study in your college course on probability and statistics, and in fact we'll cover in this course on Thursday and Friday. Ordinary least squares regression has several assumptions, but the two that are most challenged in this analysis are first that the variables should be uncorrelated. And in fact, a lot of the watershed variables can have cross correlation with each other. And even more so, the flood records that we use to predict skew coefficient in each of these gauges can also be correlated with each other. Right. The second assumption that can be challenged is that the data points are of similar quality, right? That the error is similar for each of the data points in the analysis. Now that's challenged especially for a skew coefficient because each of these gauges that are going to be in the analysis will have a different record length and therefore have a different mean square error. And additionally, each of the skew values that are computed for each of the gauges will be different and therefore have a different mean square error. So the second assumption is challenged even more. So there are other types of regression that can help with some of those assumptions. So ordinary least squares regression is going to ignore the errors in the estimated skews, and it's going to ignore any cross correlations that exist. There's a method called weighted least squares that will recognize the differing errors that come from the different mean square error of the station skew estimates based on different record lengths. But weighted least squares will ignore the cross correlation. Finally, there's generalized least squares, which recognizes the entire error structure, and that's probably the most promising approach. An additional and very important point is that the weighted least squares and the generalized least squares approach both give a better estimate of the accuracy of the relationships that are developed than the ordinary least squares will. And the accuracy is extremely important because the accuracy is translated as the mean square error, and the mean square error is what goes into the skew weighting equation. So regional skews that have a lower mean square error are going to be much stronger in the weighting equation versus station skews. So here's a regional skew study from back in 1986 that shows us some important points. This was based on 62 stations in Illinois, drainage areas up to almost 10,000 square miles. The explanatory variables used were area, channel slope, percent lakes and ponds, forest cover, soils index, and some basin indicator variables that just said it's either this basin or it's not. Some of the results were really interesting in what was similar and what was not similar between the different approaches. So they found their best ordinary least squares equation and they found the best weighted least squares equation. They found that the same variables were chosen and the coefficients were extremely similar from one to the next. But what was very different was the mean square error. The ordinary least squares showed a mean square error of regression of 0.45, and the weighted least squares showed a mean square error of regression of only 0.1, right, which is about a quarter the size of the mean square error of the ordinary least squares. So the same prediction equation, or at least close, but a much, much smaller prediction error. right? So the result of the study, coefficients were similar, chosen variables were similar, but the ordinary least squares seems to have overestimated the variance of prediction and therefore underweights the regional skew. Right, so studies that were done in the past with a simpler method would have had a higher mean square error and so a lower weighting of the regional skew in the weighted skew equation. So the approach for Bulletin 17C is recommending the use of even a one step beyond generalized least squares using Bayesian generalized least squares. But instead of recommending it be done by each analyst or each agency, the USGS has decided to perform regional skew studies across the entire United States, one region at a time. Right here is a mostly updated skew study map. This is from February 2021. The red areas have studies that are completed and already published. The yellow areas have studies that are completed and the publication is in process. The white areas, the studies are in progress, and the green areas, the studies are planned. Okay, now this link takes you to the reports. Although myself, I actually just search Skew Studies USGS 17C to find them. They're published on a page that has the reports broken down by state, right? So you scroll through the states and it links to the report for that state. And it might have been done just for that state, or that state might be part of one of those regions. Okay, some results from these are several years out of date at this point, but they show some very interesting outcomes. What we have in this table is, first of all, starting with Bulletin 17B, because these studies were being compared to the skew map in Bulletin 17B, Plate 1. And then we have some other studies that were done by USGS. And the columns, we have skew, we have mean square error, we have equivalent record length. And the equivalent record length is based on using the regional skew in the skew weighting formula. So it's how many years of record of a station skew it would balance against. Right, then there's the number of sites and the average record length. So as we've already seen, the Bulletin 17B skew map had a mean square error of about 0.3, and that is worth an equivalent record of about 17 years, which in itself is very interesting to note. Not very strong against any station skews, right? Now, here's several of the regional skew studies, and another really interesting outcome is that of all of these studies, the only one that produced a regression equation other than a constant was California. And California was the only one that produced an equation, and it was based on watershed elevation. All of the other studies produced the best equation being simply a constant, which was rather surprising. But also more interesting is the mean square errors are all about half the size of the mean square error of the skew map. Right, half the size or less, and the equivalent record lengths are quite a bit longer than the 17 years provided by the skew maps. So what this means is in the future, when we're doing studies that include a regional skew and therefore a weighted skew, those skews are going to have a lot more influence on our fitted frequency curves. So that is the end of the fourth video. When you look at these slides, you'll also find a longer list of references to read some of these background information for the skew studies. And also I recommend going to the USGS sites and looking at some of those reports. Right, so that's the end of the fourth video of the regional skew lecture. And thank you for hanging in there.